when we work with linear programs in a computer, it's easier to use equalities instead of inequalities. And to represent the linear program without inequalities, we introduce additional variables. Before we had, for instance, on this row, we had this part was less than b0. Instead, we move it over here and say that this new variable is equal to this. And then if we say that this variable must be non-negative, then we have the same linear program. So this is just a different form. These variables are called slack variables. Another term, or actually two more terms, is that we have basic variables and non-basic variables. Basic variables are those to the left here. As it happens, the basic variables are all slack variables, but that is just when we start. So the slack variables will be moved here sometimes. And a decision variable, I mean these which are originally to the right hand side, they will become basic variables. So a variable is always either a decision variable or a slack variable, and they sometimes are basic variables and sometimes other times are non-basic variables. But the basic variables are always to the left, and those to the right are always they are the non-basic variables. And in the objective function there are no basic variables, only non-basic variables. So let's see our example again. We start with this and introduce the slack variables, so we get this instead. We also have, we could say +0 here, and that's what we do when we introduce y, which initially is 0. And eventually y will be the optimal value of z. So this is 0, but it will become a non-zero later on. Okay, so what is it that we should do to maximize z? If we take a variable, a non-basic variable in the objective function, and we select one which has a positive coefficient, then if we increase that variable, then we increase the value of z. And we can be more or less clever when we select which one with the positive coefficient, but for now we just select the first one we find. And we select x0, and we want to increase that as much as possible. How much can we increase it? That's limited by these equations. And since x2, if we increase x0, we will not make x2 negative. So it's not x2. It does not limit how much we can increase x0. But x3 is clearly, if we make x0 very big, then x3 would be negative. Okay, so how much can we increase x0? We can increase it to at most 6, which will make x3 to make it 0. Okay, so what does that mean in the region that we had before? In the figure. If we started here, and the non-basic variables, they were 0. Now we want to increase x0 as much as possible. And from the figure, we can see that we can only increase it here, otherwise we go outside the region. And in the equation, we saw that we could increase x0 to at most 6, otherwise x3 would be negative, which is not permitted. So what we do is to select a non-basic variable and increase it as much as we can. That is the same as moving to a different vertex. If we only have negative coefficients in the objective function, then we cannot increase a non-basic variable. I mean, we can, but we will reduce the value of the objective function. So then we have found the optimal solution. Okay. So we stop this when all the coefficients of the non-basic variables in the objective function are negative. And then we will have the optimal value as the number here. There is a constant for y. Okay, so when we increase x0 as much as possible, what we will do is to switch places between a basic variable and a non-basic variable. And we switch places between we selected a non-basic variable with the positive coefficient. And then the question is, which basic variable should we switch with? It is the one which is constrains how much we can increase the non-basic variable the most. And we will drive that one to 0 by increasing the non-basic as much as possible. So what we will do now is to simply rewrite this. So x3 will be up here and x0 will be there. How can we do that? Well, we will simply rewrite x0 as an expression of the rest on this row. And then put that everywhere that x0 was used before. Okay, we will see how that works. Okay, so we call the one that we selected, the non-basic that we selected, as the entering basic variable, and the one that was most limited as the leaving basic variable. Okay, so what we do is to take this row and write x0 equals, we rewrite it in terms of x0 and we get this. And then we put this everywhere that we had x0 before. That means there and there. Okay, so now the system looks like this. And where are we? Well, we are at this point. We are here. Can we increase the value even more? Well, if we increase x1, then we will increase z. So let's do that. And then the question is, which one is most restricted? We have, it's either x0 or x2, which is most restricted. And it turns out that it's x2, which is the one which is most restricted, which we can quite easily realize. And therefore we will swap x1 and x2. And we do exactly the same, express x1 in terms of the rest of this equation and put that wherever we had x1 before. So now the system looks like this. And what has happened? Well, what has happened is that all of the coefficients in the objective function, they are negative. So it does not help us in a way to increase either x3 or x2. that would only reduce the value of the objective function. And now this constant, it has become 16. Then we can see that if we set, well, what should we set the variables to? If we set x2 and x3 to 0, then we maximize z. So we do that, and all of this will be 0, and x0 will then be 4, and x1 will be 6. Okay, so what is that? It is this point. Okay. In this system, it turned out that the decision variables became the basic variables in the end. That's not necessarily the case. And if a decision variable is a non-basic variable, then it will be 0. Okay? So, what we do, we start in a vertex and then go to a neighboring vertex. And we continue until all the coefficients are negative, and then we have found the optimal solution. As I mentioned, well, I didn't say his name, but he's the most famous person in linear programming. And this, according to some reliable sources, this was the killer app. A killer app is a software program which sells hardware. Okay, so this was the killer app in the 60s to sell expensive computers for companies to make linear programming. I mean to use linear programming to decide how to plan their production, etc.